Okay, in this video, we're going to talk about how to find derivatives using differentiation rules. Now, first of all, the word differentiation is just the process of finding a derivative. So we're using differentiation rules. And so we start with the constant rule. If f of x is equal to a constant, I'll just call it k, then the derivative of that is equal to 0. Now this is really easy to see because we know that a constant is just a horizontal line at whatever that number k is. And so if we take the derivative of that, remember we're finding the slope of the tangent line. Well, any tangent line would also be horizontal, and that would have a slope of 0. A linear function, f of x equals k times x, has a derivative of k. And again, that's pretty easy to see, that if we have some linear function, k times x, now that would just be some line where the slope is k, and if we just have a line here, then the any tangent line would also have exactly the same shape, and that would also have a slope of k. And so the slope of the tangent line is k, and so we got the linear function rule. The linearization rule. Now what this says is that if we have something like some number a times f of x plus some other number b times g of x, then what we do when we find the derivative is we just leave these constants out here. The constants, we're just going to leave them there and multiply it by the derivative of the function part. So the derivative of this would be a times f prime of x plus b times g prime of x. The power rule. If we have a function in the form x to the nth power, then when we take the derivative, the power, the exponent up here, comes out in front and gets multiplied by this, and we subtract 1 from the exponent. So the derivative here is f prime of x equals n times x to the n minus 1. And then the sine and cosine rule. And the rule here is that sine of x, when we take the derivative of sine of x, we get cosine of x. And if we take the derivative of cosine of x, then we get negative sine of x. And you have to kind of remember here, this is negative sine of x. Sometimes it's easy to remember to forget that we've got to include this negative sign here. Okay, so let's start off with a few examples. Let a of x equal x squared. And we want to find dA dx. Okay, now this is just another notation for the derivative right here. This is really just a prime is what we're doing. There are different notations. This is called the Leibniz notation. And so we want to find this derivative. Okay, I'm going to go back to a prime. Let's see here, the derivative. Now I see that I could use the power rule here. This is x to the second power. And the power rule says that if you have x to the n, just bring the n out front and subtract the exponent by 1. So it looks like this would be 2 times x to the 2 minus 1, which would just give me a 1 up here. And that's just 2 times x. And that's my derivative. So let's look at some other examples. Suppose we want to find the derivative of f of x equals pi. All right, remember now pi is a constant. And so the constant rule tells us that the derivative of a constant is 0. And so this is a pretty easy one here. Now, sometimes these can be a little bit tricky. You know, I mean, if this was written as something like, I don't know, pi squared or something like that, it's easy to forget that, oh, that's also a constant. Sometimes you say, oh, well, I'm going to use the power rule here, but that wouldn't be right because pi squared is also a constant. So just watch out. If it's a constant, doesn't matter if there's exponents or anything like that, the derivative would always be 0. F of x equals 5 times x plus 9, and I want to find the derivative here. Well, remember the linearization rule says that if you have things added and subtracted here, we're just going to sort of take these one at a time here. And so 5x, the derivative of 5x, would just be 5. If you have a constant times x, then the derivative would just be that constant. Plus, okay, now let's think about the 9. Well, 9 is a constant, and so the derivative of a constant sitting there all by itself is 0. And so it looks like we end up with 5 as the derivative here. All right, let's move on to the next one. We have h of z equals z to the 7 minus 3 times z to the 4th. And I want to find the derivative. All right, I'm going to take these one term at a time. Z to the 7th, well, this is just a power rule thing here, so that would be 7 times Z to the 6th. Minus, okay, so the linearization rule says that if you have a constant out here in front, multiplied by a function, just leave the constant alone, just leave it there. So I'm just going to leave that 3 out there in front and take the derivative of the function part. So Z to the 4th, the power rule tells me that would be 4 times Z cubed. And it looks like after we clean this up a little bit, we end up with 7 times Z to the 6th minus 12 times Z cubed. And we've got it. All right, I want to do the derivative of A of t equals 10 times t to the negative 2 minus 10 times t squared plus 4 times sine t. All right, I'm just going to take this sort of one term at a time. So it looks like here I've got the power rule that I'm going to have to think about here. I've got t to the negative 2. Now I know that negative 2 is going to come out here in front, and there's already a 10 out there. And so I'm going to go ahead and multiply those to get a negative 20. Now I subtract 1 from the exponent. Okay. I do the same thing here. I've got a negative 10 out front. I've got a t squared. That 2 is about to come out here in front. I'm just going to multiply by what's already out there. Subtract the exponent by 1. That would give me a t to the 1st. I've got a 4 times, let's see, sine of t. The derivative of sine is cosine. And so I found my derivative here. Okay, so let's remember just a couple of rules from algebra real quick. Remember that if I have a negative exponent, say I've got something like b to the negative n, really that's just saying just take the reciprocal here. B to the negative n is the same as 1 over b to the n. In other words, a negative exponent means that if it's up in the numerator, take that thing downstairs. If it was in the denominator, I would take it upstairs. Also remember, b to the m over n, if I've got rational exponents here, b to the m over n, this would be the same thing as the nth root of b to the m, which also could be written as the nth root of b all to the m. Okay, so I could write it either way. But sometimes what we'll do here in calculus is we need to sort of rewrite our function before we can go in and use some of our derivative rules. And so let's look at an example of some of these. Here we have g of x equals 2 over x to the 4th. And I want to find the derivative here. Well, my first step is going to be to rewrite this so that it fits one of those rules that we've seen here. I don't really have a rule that fits exactly what's going on here in its present form yet, but I know I could rewrite this as 2x to the negative 4. And now it fits with one of our rules. I can find g prime of x is equal to, let's see, the power rule says to take the negative 4, bring it out in front. I'm going to go ahead and multiply by the 2 that's already out there. Subtract the exponent by 1, and I've got my derivative. Now there's nothing wrong with this derivative here, but you know sometimes we need to be able to write these things in different ways. So remember there's other ways that this could be written. This could be written as negative 8 over x to the 5th, just by taking care of that negative exponent right there, bringing that downstairs. So just be aware that sometimes we'll write the derivative in different ways for different reasons. Let's find the derivative of this one right here. F of x equals the cube root of x squared. Okay, in its present form, I'm kind of stuck. I can't really go in and do the derivative directly because I don't really have a rule that deals with this. But I can rewrite this function. The cube root of x squared is the same thing as x to the 2/3. All right, and that's just using this property right up here from algebra. So x to the 2/3, I can use the power rule on that. F of x equals, let's see, the exponent comes out in front, so I get a 2/3 out here in front. I'm going to subtract the exponent by 1, which would give me a negative 1/3. Okay, and so I found my derivative. The rest of this is just algebra. You know, there's nothing wrong with this expression as it is, but sometimes we have to rewrite things in different ways. Let's see, that's a negative exponent, so that goes downstairs. So I can rewrite this as 2 over 3x to the 1/3. I could even take it one step further. 2 over 3 times the cube root of x. You know, I'm just showing you this because, like I said, these are all equivalent. There's nothing wrong with any of them. But, you know, when you're taking quizzes and things, sometimes you have, you know, answer choices that are given to you, and it may not be in this form. It may be in this form, and you need to be able to recognize that those things are the same thing. Okay, let's look at another example here. All right. Okay, so these are getting a little more complicated, little by little. But you know, when you look at this, well, yeah, it looks kind of complicated, but we know how to deal with each one of these things individually. I've got a radical here, and I know how to deal with those. I've got a fraction here where, you know, I've got the x in the denominator. I know how to deal with those. And the rest of these things are pretty straightforward. So my first step is I'm going to go in here, and I'm just going to rewrite this function. Now, I'm not doing the derivative yet. So don't get your notations mixed up. Don't call this f prime because we're not doing the derivative yet. All we're doing is rewriting the function. And so I know this is the same thing as x to the 1/4. I know that this one is the same thing as x to the -2 minus 7x cubed plus 12x minus 16 cosine x. Okay, so I've just rewritten my function. But now I'm able to go in and find the derivative because I've got everything in the proper form. F prime of x is equal to, okay, I'm going to bring the 1/4 out front and subtract the exponent by 1. Let's see, I've got x to the -2. I'm going to take the -2 and bring it out front and subtract the exponent by 1. I've got negative 7x cubed, so the 3 comes out in front, giving me negative 21x squared. 12x is just a constant times x, so that's going to give me 12. The negative 16 is going to stay where it is, and the derivative of cosine is negative sine x. So we've done the derivative. Anything else we do here is really just going to be rewriting this using algebra rules. It may be that we just leave the answer like that, but again, sometimes we have to write these things in different ways for different reasons. So let me just go in here and clean this up a little bit and see what that would look like. I've got a 1/4. This x to the 3/4, negative 3/4, that's going to come downstairs to give me x to the 3/4, which is the 4th root of x cubed. All right, this would be -2, and I'm going to bring this downstairs, so that's going to be minus 2 over x cubed minus 21x squared plus 12. It looks like the only other thing here is I can multiply these two negatives to get a positive 16 sine x. And that's about as simplified as that gets. Okay, let's look at another example. All right, here what I want to do is I want to find all the values of x. I want to find all the values of x where f of x equals 3x cubed minus 144x has a horizontal tangent line. All right, now let's remember, when I have a function, I can think about any point on this function, any point along the graph of this, and the slope of the line that's tangent to that point is what the derivative is giving me. And so I want to know all the values of x where I have a horizontal tangent line to this function right here. So that's saying I want the tangent line to be horizontal. I want it to be straight across. I want it to have a slope of 0. So this is really just asking, hey, where's all the places where the derivative of this is equal to 0? And so let me just kind of write that out. Horizontal tangent line. What this is really meaning is I want the derivative to equal 0. All right, so first thing we got to do is find the derivative. I've got 3x cubed minus 144x. That's a pretty straightforward one here. It looks like that will give me 9x squared minus 144. And I want to set this equal to 0 to see what values of x make that happen. Okay, so I'm going to, let's see, factor out 9. That gives me x squared minus 16 equals 0. X squared minus 16 is a difference of squares. I can rewrite that as x minus 4 times x plus 4. And to set this equal to 0, I'm just going to set each one of these different factors equal to 0. And when I set 9 equal to 0, I don't get anything from that. That's not true. It just doesn't give me any x values. When I set x minus 4 equal to 0, I get x equals 4. And when I set x plus 4 equal to 0, I get x equals negative 4. So it looks like the values of x that makes this thing have a horizontal tangent line would be at 4 and negative 4. And if I go in here and just take a look at this in my calculator, I've put my y value in, my function in here into the y equals. I'm going to use something like x is going to go from negative 8 to positive 8. Y is going to go from negative 800 to positive 800. I just played around with some numbers to get that. If I look at the graph of this, I can see here at negative 4, you can see what's going on there. That's at that very top point right there. That tangent line would be horizontal there. And also the same thing happens here at positive 4. And so I can see that that's really coinciding with what it is that I'm finding right here. So what is it that I'm really doing here with these derivatives? Well, let's just kind of think about this for a second. The derivative of a function is a function itself. And that function represents the instantaneous rate of change at which the function is changing with respect to x, or whatever variable I'm dealing with. So suppose that the following function represents the cost in thousands of producing x hundred pieces of computer equipment. The rate of change, which would be cost per unit, is represented by the slope of the tangent line at any point on the graph. I want to compare the cost per unit for when less than 100 units are produced, and the cost per unit for when more than 100 units are produced. Okay, so remember x is in hundreds right here, so this is where 100 units is produced right here. And so I want to know, well, this is the cost. Okay, so this is the cost of producing this many units of computer down here. So if I'm less than 100, then I'm talking about what's going on over here. Let's just pick a point over here, like maybe right about here. And I look at the tangent line there, and I don't know what the slope of that is, but I can see that that's a fairly steep line right there. That's got a pretty good incline to it. And so I can see that the cost for producing each one of these computers when I produce fewer of them is pretty high. Whereas if I'm producing a lot of these things, then I'm looking at points out here somewhere. Let me just pick one out here somewhere and look at the tangent line to that. And I can see here that the costs per unit for producing a lot of these this computer equipment is less, because the tangent line would have a smaller slope. And so this is just sort of just cementing the idea of what a derivative is. What does it represent? It's representing the instantaneous rate of change of whatever y is with respect to x over here. And you do that by thinking about the graph of that function and thinking about points on that, and then saying, well, what would the tangent line look like there? And more importantly, what would the slope of that tangent line look like? Okay, so I hope that this has been helpful. It's important to remember these different formulas for the derivative, because this is definitely the way to do it. It's a lot easier than going back to that definition of derivative that we had before. And what we'll do in the next video is we will talk about some more, a little bit more complicated formulas that we'll have for different types of functions.